And welcome to the next lesson in our distance learning series. Still doing physics. I hope you all had a good Easter break and are ready to carry on. I thought I'd do these ever so slightly different this time. They're going to be going to talk through the presentation. Hopefully it'll make things a little easier for you guys. You won't have to look through two different documents. When we get up to bits that I'd rather draw out or explain, as I've done previously, I'll splice a couple of videos together, as I have spent Easter learning how to do that. Okay, another bonus of doing it this way is we can start with 5 starter questions. These are the same 5 questions that are on your assessment set of questions that goes with this, so you might want to have that open separately so you can answer as you go, or you can just be doing that on a pen and paper, or indeed just in your head if that's what works best for you. Okay, so first question then is, state the equation that links force, mass and acceleration. 2, what is the equation for speed? 3, what is the unit for force? 4, state Newton's third law. 5, state the electronic configuration of neon. So you need to be looking at these numbers here, remembering which one's which to be able to work it out. And then 6, what process takes place in the mitochondria. So answers: the equation that links force, mass, acceleration is force equals mass times acceleration. Speed equals distance divided by time. The unit of force is newtons. Newton's third law is every force has an equal but opposite force. Electronic configuration is 2, 8. That's 2 electrons in the first shell, 8 electrons in the shell after that. So we would find neon in group 8, period 2, and then it's respiration that takes place in the mitochondria. Good. Common exam question is, why do muscle cells have more mitochondria than other cells? Because your muscles do work, your muscles require more energy, respiration is what makes energy, and so they need lots more mitochondria. So we're going to look at gravity today. This should be something that you might have seen before, you might have covered before in your previous schools. It's a nice simple topic, nice simple bit of work to do today, where we've got to understand the differences between mass and weight, and then look at doing these calculations of force exerted by gravity. Okay. So really the key to this topic is this first bit here. What is the difference between weight and mass? And if we think about what we know about space, what we know about gravity, when people are in space, when people go up into space, they float around, and they float around because there's no gravity in space. And so we say that people in space are weightless, that they are without weight. We can't, however, say that they are without mass. And that's really the key difference between these two things. Mass is the amount of stuff within an object. It remains the same no matter what. So me, you, the chair you're sat on, the room you're in, they all have mass, and we can move those around. We can take those things into space, we can take them to different planets, and there will always be the same amount of mass there. Whereas your weight, it is dependent on gravity. So the weight is the force you exert on the ground you're on, or the chair that you're on, and that's very much dependent on gravity. it's gravity that determines whether you have weight or not. Your mass is fixed. Okay. If you go deeper underwater, there's more mass pushing down on you, and so it's harder to move around. You feel like everything weighs more and it's more of a struggle to move. You experience that just a little bit if you go in the deep end of a swimming pool. The further down in the ocean you go, the harder it is to move around. Okay. Okay. And planets all have a gravitational field, and it's that gravity that pushes objects into the planet. So Earth has a certain gravitational field and it's pushing us down into it. Other planets have their own gravitational field that might be more or less. In actual fact, every object has its own gravitational field. You have a small gravitational field. Your mobile phone has a small gravitational field. It's just that it's very, very small, because the gravitational field that an object has is dependent on its mass. Okay, the bigger the mass, the greater the force of gravity. So the sun, being very, very, very big, has lots and lots of gravity, and that's why all the planets in the solar system are stuck to it. They're pulled into it by gravity, including Earth. My drawing's not very accurate here because there's a couple of other planets in between the sun and Earth, but we are held to the sun by gravity, and we're all held on Earth by gravity too. And the moon has its own gravitational field as well. It's much, much smaller than the Earth's because the moon's much, much smaller, and it's the Earth's gravitational field that keeps the moon stuck to it, the sun's gravitational field that keeps the Earth stuck to the sun. The moon's gravitational field, while small, it is strong enough to affect Earth, and it's why the moon controls our tides. When the moon moves, so do our tides, and so that's what causes the water to go in and out. It's the moon's gravitational field working on Earth. Okay, so see that a little bit closer here, my lovely picture. Don't say that I'm not doing anything with all the time on my hands. Okay, so we can look at what happens if we increase the Earth's gravitational field here through this video. I do not know what happens if you watch a YouTube video on a YouTube video, so we will see what happens.
Gravity may be weak here on Earth, but it's not so weak across the cosmos. This invisible force varies on all the planets in the solar system and on the exoplanets we've discovered orbiting other suns. To experience what gravity feels like on these worlds, I need to go for a spin. This is a centrifuge. It was built in the 1950s to test whether fighter pilots had the right stuff. But it's going to allow me to feel what it'd be like to stand on the surface of any of the planets in the solar system that are more massive than the Earth. And in fact, also what it'd be like to stand on some of the planets that we found around distant stars.
Okay, so larger planets would have a greater gravitational field. If you were to go on them, it would have some adverse effects on your body, which you will see in just a moment.
All right, I'll have to strap you in, first of all. Let me see the roller. This one here. This isn't going to go switch. It's an emergency switch in case something happens and you release it, the centrifuge will stop. I was just told by the F-16 fighter pilot who's just been in here that it's 100 times more uncomfortable than being in a jet fighter. And I was kind of confident because I've been in jet fighters and didn't find it too uncomfortable, but apparently this is 100 times worse.
Doors closed again, profile is there, safe limits are there, doctor is ready. We'll start up the centrifuge, Brian, and bring you in orbit. And it happens in 3, 2, 1 second from now.
The first planet I'm travelling to is Neptune. Its gravity is just fractionally stronger than here on Earth. This is the gravitational field on Neptune, and you feel, you know what, I could probably get used to this. I could probably live on the surface of Neptune.
Can you lift your hands a little?
There we go.
Yeah, and down.
And it is actually quite an effort. It isn't.
Okay, because gravity is ever so slightly greater, everything weighs slightly more, including your arms. So lifting your arms will feel as though they're heavier because there's a greater force pushing down on them. There's a greater force of gravity trying to keep them in their place. Neptune's ever so slightly bigger than Earth, so it has ever so slightly greater gravity.
Noticeably heavier. It's like having a reasonably heavy weight in your hand.
You ready to go to 2.5 G?
Yes, and I will move from Neptune to Jupiter.
Let's go there.
Jupiter is over 1,300 times more massive than the Earth, but because it's mostly gas, it's not very dense, so its gravity is just over twice as strong at its surface. Well, now actually it is quite difficult to lift my hand, and that's 2.5 G. I wouldn't want to sit here for half an hour.
And can you lift both of your hands above your head? See what happens there.
Let's see. So actually, just about, but actually it's an immense amount of hard work. So it would be hard work living on Jupiter.
Let's go to 4G.
Actually, this is heading to a planet around a planet called Ogle 2 TR L9b, which is around a star in the constellation of Carina. It's one of the exoplanets we've discovered. Oh, and there we go.
Okay, and you can see the effect that this greater gravity is starting to have on Brian here. You can see his eyes are sagging, his face is sagging, and that's because the extra gravity is pushing all his skin down. Your muscles in your face are designed to work with normal amount of gravity. This greater gravity means they're not strong enough to keep everything in its place, and so you go a bit saggy.
Actually beginning to feel quite unpleasant.
Can you describe what you're feeling?
A very heavy face.
All right.
My head is extremely heavy.
How about your lungs? Inhaling, exhaling, breathing?
It's much harder work. I can't lift my hand off my leg.
Okay.
And that's at 4G.
Yeah.
But my head and my face feel very, very heavy.
Yeah.
It's quite an unpleasant feeling.
We'll go to 5 and let me know if you have any visual disturbances.
I'm now en route to a newly discovered exoplanet, WASP-8b. 4.4. This world sits in the small and faint constellation of Sculptor. Quite hard to speak. It has a gravitational force nearly 5 times that of the Earth.
All right, we're going to 5G.
Very foggy.
Okay.
Okay, so he starts to report visual disturbances and difficult staying conscious. This is because that extra gravity is not just pushing on his muscles, which it means his face looks like this, but it's also pushing on his lungs, which means he can't get the amount of oxygen in he requires. which means he's struggling to respire, and so things start to stop working. And that's why his sight goes, if you continued at this, you'd start to lose consciousness and pass out, hence the need for the switch they mentioned at the beginning.
Very foggy. Very foggy. Still foggy?
Yeah.
All right.
Take it down.
Okay, we'll take you down.
Okay. And as the gravity drops back down and quickly return to normal, there's no great long-lasting effects of this. Okay, good. So the important thing to take from that video is that the force of gravity relates to your weight. It relates to how easy it is to move around, because it is effectively changing the amount of weight you have. And your weight can go up as well as go down. We think of space as making us weightless, making us able to float around, but bigger planets would mean that we were, the opposite would happen. We would feel heavier. And we have an equation that links these two things together. This is one of those equations you need to learn, you need to be able to use, and it looks like this. Okay, so gravity force is equal to mass times gravitational field strength, and it's this gravity force here. This is weight. So in my shorthand for it, we give that a W for weight. And gravitational field strength is what we think of as gravity. So how much is gravity on Earth or on different planets? My mass is fixed. This is however much an object or a person weighs. The gravitational field strength is fixed to a particular planet. And then gravity force is essentially weight, and it's measured in newtons. So it's how much force you're exerting on the ground right now. And that's what we think of as being our weight. Okay? And we can have a triangle for that if you like it. And the important thing to know, or an important thing to know about this, is that on Earth, the gravitational field strength is 10 newtons per kilogram. Okay, and that's one of those little things that you need to remember. Luckily, it's a nice, easy number to remember, the number 10. So if you're ever asked to do one of these calculations, you might be expected to know that if it tells you the experiment or the test is taking place on Earth, that your gravitational field strength is 10. Okay. If you search it online, you'll find that there are lots of different numbers for this. Lots of them are quoted as 9.8 and variations, but 10 is the number that you need to remember. It's the easiest number to remember. Okay, and just know that gravitational force or weight can all be used interchangeably within this here. Good. So we're going to look at a couple of examples of this. I will swap over and complete these by hand. And here we have the first of those example questions to have a little go at. So what is the weight in newtons of a 2 kilogram chicken on Earth? And this is quite a nice question in that it tells you that you need to be looking at newtons. So it's reminding you that you're thinking of a force. It gives you a mass, it gives you the units to remind you of. The only thing that it's being slightly tricky about is it's not giving you the force of gravity on Earth, but that's pretty expected with questions like this. Hopefully you're enjoying my tablecloth here, very retro, and the state of my hands from all this constant hand washing, which I hope you're all doing. So, question like this, couple of marks. First thing you want to do is write out your equation, make sure you show that you know it. You are just going to have to commit to learning these equations, I'm afraid. So weight equals mass times gravity. And when you're writing out these equations, you don't need to worry massively about writing it out beautifully. Just make it really clear that you know what it is that you're going to do. And then write out the terms of it. Weight, mass, gravity. Okay. And then go through and say which each of them are. So your weight, that is my thing that I don't know, so I'm going to put it as a question mark. My mass, it tells me, is 2 kilograms. It's good to write the units because this needs to be in kilograms. So if it's in grams, you're going to need to convert it. And then gravity, it's 10, and it's in Newton kilograms, which is why this needs to be in kilograms as well. But you just need to know that it's 10. So nice and simply then, it's a case of putting these numbers into your equation. So 2 times by 10 equals 20. Okay, and then your units for weight, it's a force, so it's in newtons. Okay. So that might only be 1 or 2 marks in an exam question because it's not asking you to do too much, but you get a mark for showing your equation and then a mark for sticking your numbers into it. You need to rearrange an equation ever, you'll get more marks for doing that. Okay, so when you're answering the questions on your assignment in a minute, look at the number of marks. They're a clue to how much you need to do. Good, so then second example question. What is the weight of the same chicken on a planet with a gravitational field strength 5 times greater than that of Earth? So my chicken's looking a little bit ropey here. It says it's on a different planet, so it probably needs a space helmet of some kind. Yeah, I'm not, despite my best efforts, my drawing skills have not improved any for being in isolation. But there you go, there's my space chicken. I'll make it nice and clear. NASA chicken. So because this is asking you to do something a little extra, you'd get a couple more marks for it. Still, make sure equation goes first. Force, mass times gravity. They like to change up what this is, so they can talk about it in terms of force, they can talk about it in terms of weight, they can talk about it in terms of a combination of those. Just if it's talking about field strength, it's talking about weight or mass in some way, this is the equation you need to know. So force, again, we're not sure on. The mass, it's the same as previously. My chicken hasn't changed mass for being on a different planet. It's still 2 kilograms. And with questions like this, when it's multiple parts of the same question, you are often expected to go back to the previous one. So if you're looking at these questions, the ones on your assignment in exams and you're struggling, think back to the question before it, look back and see whether you can get any numbers from that. And then gravity, it's 5 times greater than on Earth, so 5 times 10 is 50. Okay, and then sticking those numbers into your equation again, your force is equal to 5 times 10 equals 50, and it's newtons because it's a force. So your chicken would feel like it weighs a little bit more on this planet. To try and pick it up would be an awful lot more difficult. You ever have to rearrange this equation, which you do for your assignments, for your questions that you're doing in a minute, just remember it's weight, force on top, mass, gravity underneath. Cover the one you don't know and go from there. So covering, if you need to find your mass, you're going to need to be doing weight divided by gravity. If you need to find your gravity, it's weight divided by mass. Okay, good luck, have a go at those, make sure they're all done before your next lesson, which will be in a couple of days' time. Thanks very much, bye bye.